I assume that for some of you, RStudio may be new. So if you open it for the first time, this is what it will look like. And now we can open the file here. So let's start right away. What is even a time series? A time series is a data set in which one row contains a measurement value and another one contains the point in time when this value was measured. The most common forms of time series are cases where data is measured yearly, monthly, or daily, but every unit of time could be used. Now, to be able to work with time series in R, we need some packages. I have listed them here. If you try to work with the tutorial for yourself, you will probably have to install them first, but I have already installed them. So I just load them with the library command. And one of these packages also includes the time series data we will work with. We can take a look at it in the environment here by giving it the name Australian production, and we can see that this object now appeared here. We can also use R to show the first rows of this table, and I think this will make clearer how a time series could look like. So what we have here are goods produced in Australia, for example, how much beer was produced in Australia, how much tobacco, and so on. And the time information. In this case, the data set is quarterly. So for every year, there are 4 entries, one for the first quarter, one for the second, one for the third, one for the fourth, and afterwards, the next year starts. Now, this column is a bit particular because it contains the time information. We will have to make sure that R correctly recognizes that this is the column with the time information when we conduct time series. And for R to work with time series, there is a special class called a fable. And the fable is a special type of data frame or table. You can verify that this data set we have here is correctly recognized as a fable by looking at which class it has. And as you can see here, there is this part which says that we are looking at something called a table time series. In case you have a data set that is not recognized as a fable right away, you can turn it into one. To do that, you will need to specify which column contains the time information. As an example, I just created this very, very small data set. If we take a look at it, we see that it only has 2 columns. I called them time and value, and only 2 rows. And if we look at the class, we can see that it is a data frame, it is a table, but it is not recognized as a time series, even though this column is even called time. Now, if we want to make sure that it is recognized as containing a time series, we will have to turn it into a fable. And there is the fable command for it, which requires us to define which column contains the information on the time. So we run the fable command, and now we can see that the modified table is correctly recognized as table time series. Even though if we open the two and compare them, we will see that they contain exactly the same input. So this is just about telling the system where to find the time variable. As I mentioned in the announcement text, this tutorial will focus on the so-called ARIMA model. The ARIMA model as a whole can take on quite complex forms, but it is a form of regression, and I think it's more easy to understand if you look at it piece by piece. Now, hopefully all of you are familiar with ordinary linear regression, which is depicted in formulas such as this one. You have an explanatory variable x, you have an explained variable y, and you calculate this beta to explain the relationship between the two. Beta can be positive, then an increase in x means an increase in y. Beta can be negative, then an increase in x means a decrease in y. And you can also try to predict y once you have calculated the beta, because on average, for ordinary least squares, y should be x multiplied by beta. This is really completely accurate though, because we have this error term epsilon, but you can calculate the beta to minimize this error term, and then the error will be 0 on average in most well-behaved data sets, so to say. One would also expect the error term to take on a normal distribution, but at least its mean should be 0. If it is not 0, you can also simply include a constant. Now, for a time series analysis, what we can do is that we replace x by y values from previous time periods. This is called autoregression because we explain a variable using its own past values. And this is where the AR in ARIMA comes from. So the simplest form of such an autoregressive model is to say we have a value of today of the y variable, and we will predict it using the value from the last period. Again, we have this beta, which tells us about the size and the direction of the influence, and again we have an error term. And of course, in such a model, they all need to have an index t, because you have to know in which time period you are. What you can also do is using this model for forecasting. In this case, again, you assume the error term to be 0, and then a good guess for the future will be that the future is the last known value multiplied with the beta you calculated from past values. Like the ordinary linear regression model, you can easily expand such a model using more than one explanatory variable, or in the case of time series analysis, more past time periods. There's one more thing we can do that we cannot do in ordinary linear regression, which is to include past error values. Because if we have a model that gives us the relationship between the current y and the past y, we can use the same model to model the relationship between the y from last season and the y from the season before. In this case, since we know the y variable's values on both sides and we know the beta, we can also calculate what the actual error term was like. So as soon as this ET has a past index like t minus 1 or t minus 2, it is no longer a random variable because this is a past error that has happened. We can observe it and simply include it in the data for future predictions. And this variant of the model, which includes past errors, is called autoregressive moving average. It is called that because if you have a model which only contains this past error values, this model will have a property to predict that the y value will move towards an average. So this is where the name comes from. Now this model works well for stationary time series. Stationarity was already mentioned in the chat. It was even mentioned that there is the distinction of strong and weak stationarity, but strong stationarity is very difficult to prove. And for now, I will just stick to the note that stationary time series have a constant mean and variance. Strictly spoken, strongly stationary time series have some more properties as well, but anything has to have a constant mean and variance to be called stationary. If you remember the gas data, this is not a constant mean, and it's also obviously not a constant variance. The mean obviously increases over time, so does the variance here. The stock market data also does not look stationary. If you take the mean from this time period and compare it with the mean from this time period, obviously this mean will be higher. So it is not stationary, even though it's more difficult to describe a clear trend. And if we have this situation that we suspect a data set of not being stationary, we can also test this formally. The test for this has a fairly complex name, Kwiatkowski-Phillips-Schmidt-Shin test. And it will give a value of 0.01. Then we know that the data is not stationary. If it gives a value of 0.1, the data is most likely stationary. And we see here that for the Apple stock data, we indeed have a time series that is not stationary. So how can we make sure that the data set is stationary? To be more precise, at least weakly stationary. We do this by differentiating the data. Now, differentiating is a process that has a lot of implications, but I think it is easy to obtain an intuitive understanding of what this means by making sure that we understand you subtract the value of the previous time period from each value. To do this in R, I define a new variable. I call it diff close, so this is the differentiated closing price. You can create these new values with the mutate command. And this new value is the difference of the old one, so there is the difference comment for this. What we can see now is that for the first day, we obtain a not available. This is because we would subtract the value of the previous time period from each value. But this is the first value, so there is no previous time period in the data set, so we cannot calculate a value for this first day. But for the other days, we simply have what you get if you take this value and subtract this value from it. So here it's negative, it's -3. This is positive, but a very small value because these are nearly the same. Here we have again a positive value, and so on. In an ARIMA model, any time series that got differentiated is called an integrated time series. Integration is the opposite of differentiation. So what this ARIMA model essentially does is using an ARMA model on the differentiated data and then integrating the differentiated data to produce the forecast. So that's why it is called an integrated model. Now, there is a function for time series analysis which we can use to let R pick a model for us. We don't have to do that. We could decide by hand, for example, I want to include 2 past values, I want to include 3 past values, things like that. But from my experience, it is also interesting to see what the algorithm suggests for a model. In the past, it wasn't very accurate, but I think it has improved. Still, there is no guarantee it will always be correct. Now, before we do that, I will briefly create a new data set, which will contain the values of the Apple stock for January 2016. This will be the values we will try to predict now, and that means we can directly compare with the actual values how accurate our predictions were. Again, to ensure that the time series is not interrupted, I will continue with the day variable simply. So I start at 253 here because there were 252 observations in the previous year. Now, to fit an ARIMA model and to create a forecast, there are always 3 steps involved in R. And I think it's very important for anyone who wants to use forecasting in R to understand these 3 steps. Each of them is very simple, but one has to make sure that they are executed correctly. The first step is to fit a model. In theory, this could be any model. I only have 1.5 hours, so I focus on the ARIMA model here, but there are many other models available in different R packages. And what this function does is that it simply creates an ARIMA model based on some statistical tests. For example, it uses the Kwiatkowski-Phillips-Schmidt-Shin test we used up here to determine if the data should be differentiated. If the test gives that the time series is most likely not stationary, then the data will be differentiated. It also automatically determines how many past values and past errors to include, but you don't have to use this automatism. You can define a model by hand. We will do that later, but for now, let's just go with what the algorithm suggests. And there is the convention to call the resulting object a model fit, because you take a very general type of model, in our case an ARIMA model, and fit it to a specific data set. In our case, the closing prices from the Apple stock market data. Once you have created this fit, you can use it to create the forecast. For the forecast, you need to define how many periods in the future you want to forecast. There are two ways to do this. One way is to define a number of periods we want to forecast. We will do that later. The other way is what I do here. I have some new data and say forecast as many periods as this new data contains. And this is part of why it's so important that this new data follows exactly the same pattern as the data from the previous years. I have been working with this day variable in the analysis so far, and if I now try to use the date variable instead as time series, I would get an error message because it is a different way to define a time variable, and R can only follow one definition at a time. Now, this model, this part is as a convention given this FC ending, FC for forecast, and there the forecast is saved. After we already have the forecast, this will be an object. We won't be able to do this much initially. We need to plot it to understand it better. So here I use the autoplot function again to plot the forecast. This is the forecast object. And additionally, I add, this is the auto layer, in a gray color, the closing stock market prices from January 2016. So we have them in the same graph. Now, what you can see here is this part of the data we have already seen. We know what it looks like. This part of the data is how the stock actually developed. And this blue line is the forecast. It is not very accurate, at least I wouldn't say that it is. And it shows that not every model necessarily gives a good prediction for future values. So even though the algorithm is quite good at fitting this ARIMA model automatically, it does not necessarily mean that it will be able to give a very accurate forecast. And to understand better why that is the case, I think it's important to take a look at what the ARIMA model looks like. We can simply do that by typing its name here. As we can see, it is indeed an ARIMA model, and it is not a very complicated model. The data is integrated once, so it was differentiated, which is not surprising to us because this is what the test above already suggested should be done. So this in the middle is the integration level. What we see on the left are the AR components. So one would be that the value from one past period would be considered, two would be the values of two past periods, and so on. Likewise, the other zero is the moving average component, and informs about if any past errors were considered, and we can see this is 0 as well. So neither past errors nor past values were considered in the forecast. And that may appear strange because you may have the intuition that when you try to predict future stock market values, it would be useful to take past developments into account. But the stock market is very volatile, and it is fairly common that ARIMA models are not able to predict it very well. We can take a closer look at how the pattern looks that the model has underlying that will hopefully enable us to understand better why we get this seemingly somewhat strange result where the model simply predicts that the value of the stock might stay exactly where it was. And to do that, instead of trying to predict the absolute value of the Apple stock, so this year, we will now take a look at the differentiated data. I explained before what this differentiated data is. You can interpret it as the change from day to day, and one can also try to forecast that. The process is the same as we've seen before, except we don't use the variable close now, we don't use the closing prices now. Instead, we look at the differences in closing prices. Again, we fit the model, create and plot the forecast. We get a value about missing values because, as you hopefully remember, you take the differences from day to day, and that means that there is always this first row which has a missing value. So this warning is to be expected. And what we see when plotting this day-to-day change is that it is very volatile. It is very difficult to detect any type of pattern in here for the human eye. And the ARIMA model, again, presents a somewhat strangely looking forecast because the blue line, again, predicts no changes, even though the data in the past has obviously changed quite a lot. But what we can also see now is that the blue line is fairly close to the mean value of this whole time series. And this is the logic, so to say, behind this whole prediction. The prediction is going to have a fairly large error because from past values alone, it is not possible to predict if the price next will go up or down. But it still has a smaller error than any attempt to predict that it would go up or any attempt to predict that it would go down would have, because the data is so volatile. So in that sense, it's still not a very good or reliable forecast, but I think it's as good as the model can get. And if we take a look at what the model to predict this differentiated value now, we will see that it is no longer integrated, which makes sense. The previous model was integrated because it did not look at the differentiated data. It also does not consider any past values or any past errors. So you may wonder, is it so to say an empty model? If this is all that's in the model, then what is really left in it? And what you have in the case of such a model is something called white noise. Looking at a formula, this would be the formula of this model. You would predict that any future y values are completely random. And looking how the past values behaved, it is understandable where this comes from. In a sense, such a white noise model is the simplest ARIMA model you can have, but it is a model which just contains a single random component. So if you are trying to pinpoint an exact value, a white noise model is essentially suggesting that there is no way to somehow find a more exact future value you could forecast. As I mentioned, the previous model has an error term that makes it difficult to create more accurate forecasts, but nearly any model you use to predict any time series will have this error term. Again, this is something you should be used to from linear regression. There are some cases where something is perfectly predictable and doesn't have any error term, but these are not usually cases where you would even use linear regression as a research method. Now for time series analysis, there's something called the confidence interval, which gives you an information about how this error behaves. The confidence interval is something that you depict for different probabilities. By default, it is computed in R for 80% and 95%, but you can compute it for different values. The interpretation is fairly straightforward. If you take a look at the 80% confidence interval, it means that a future value will be within it with 80% probability. If you take a look at the 95% confidence interval, a future value will be in it with a probability of 95%, provided that your model is correct. Now, the confidence interval is normally automatically shown. Above, I use the level equals null in the autoplot function, and that's why it was not shown. But I removed it here so we can take a look at the confidence interval now. And what we can see is that the confidence interval really includes most of the values that the difference in closing price variable takes on in January 2016. There are some outliers. This is out of the confidence interval. This is out of the confidence interval. But most of these values are within the 80% confidence interval. Some are not in the 80% confidence interval, but in the 95% confidence interval. So what we can see here is that although an attempt to forecast an exact value is not very likely to give a very accurate result, this estimation of confidence intervals gives fairly reasonable forecasts. They are just the type of forecasts that can be difficult to explain to people who want deterministic answers, because their confidence intervals, of course, they are related to certain probabilities. Now, the confidence interval is constructed again based on the behavior of the formula. Keep in mind that the model we are looking at is this very simple white noise model. It is argued that yt will simply be equal to this epsilon t. And this is the error term. It will be 0 on average, as we can see here. But it also has a certain positive variance associated with it. And this variance can be calculated from the variance of previous values. The data is stationary, at least weakly stationary. So under this assumption, it's reasonable to assume that the variance in this area will be the same as the variance in this area. And this is why it's so important to take a look at stationarity when attempting forecasts. Now, this is a fairly simple confidence interval because, as I mentioned, the data is stationary, so it is assumed that the mean and the variance will not change over time. But for an integrated model, the confidence interval looks very differently. We will now take a look at the confidence interval for the absolute value of the Apple stock. And what we can see here is that the confidence interval changes over time. The data is not stationary, so it does not have a constant variance associated with it. The process that we see here is called a random walk, and it is quite typical for stock markets to follow nearly or completely this random walk pattern. Now, the random walk pattern is, as the name says, random, but it differs from white noise because it is integrated. And what does that mean? In white noise, the errors over time are not related to each other. Every day, so to say, you start with rolling the dice again. On average, you will get a 0, but you could get a positive or negative value. And more importantly, the concept of white noise says that you will get a positive or negative value regardless of what value you obtained on the previous day. So sometimes the stock value may rise 2 days after each other, sometimes it might fall on one day and rise on the other day. This difference values are independent from each other because they are white noise. The integrated values, on the other hand, depend on each other. What happens in this model is that errors sum up from one day to the next. So for the first day, you have the insecurity associated with the first period. But if you try to forecast 2 periods into the future, you have the uncertainty from the first day plus the uncertainty from the second day. For the third day, you have the uncertainty from the first day plus the uncertainty from the second day plus the uncertainty from the third day. So these uncertainties pile up. And this is while the forecast is getting more and more insecure the further we look into the future. And this is what causes this confidence interval to spread out like we see it here. I will also address something I briefly mentioned before, that if you want to create a forecast, there are different ways to define how many periods in the future you will want to do that. One way is if you have some new data to predict a forecast and then compare it to the new data to see if your forecast was accurate. This is what we have done previously. The other way is to give an information by defining this age variable. Now, it is important to consider that this variable has no clear unit, so to say. You don't tell it predict 10 years into the future or predict 10 months into the future. Instead, this variable always takes on the same unit that the data has. So in this case, it will predict 10 quarters into the future because for the Australian production data, the time series unit are quarters. If we did the same with the stock market data, it would only predict 10 days into the future because the stock market data was given daily. And I will run the code now and take a look at the forecast first. You see immediately that it is very, very different from the attempt to predict the stock market value. It's looking a lot more reasonable in the sense that it takes this fluctuating pattern of the gas production and continues it. It still has the confidence interval, but the confidence interval is no longer as broad as it used to be, and it also doesn't appear to increase much over time. What we can see here is that the model predicts that gas production will continue to increase. It also predicts that these fluctuations will continue as they did in the future. Now, for any type of model, it would be very difficult to predict structural breaks. So if you tried a forecast here, it is unlikely that you would have gotten an accurate prediction for this point. This was also one of the aspects of the COVID-19 pandemic, that the pandemic meant many forecasts were no longer valid because forecasts typically use a model first to explain patterns observed in previous data, and then you create the forecast by assuming that these patterns will continue for the future. Structural breaks still are not really possible to predict with the type of time series analysis models like ARIMA. But for data series with certain properties, like the gas data, forecasting is working very well. That having said, I mentioned that the model behind it can become fairly complex, and gas production has fairly complex pattern. So we see that it is still an ARIMA model, but it has a great number of components now. Again, we will split this up and go through it piece by piece. This is what one could call the ordinary ARIMA part. Again, we have 0 autoregressive components. Here we also don't have an integration. But now we have past error values. So for 3 past periods, this model considers the error values. Second, and this is why we have the second group of brackets here, what we are looking at now is a seasonal ARIMA model. This is something that you would usually not encounter for example, yearly data, but it is fairly common for quarterly data. Gas production is influenced by which season we have. This is maybe not immediately to see from the data because the data covers a fairly large time span, but these regular fluctuations are directly tied to the seasons. So to make an accurate prediction, the model has detected that there is the seasonal pattern. The number of seasons is in these brackets, and the model correctly predicted that there are 4 seasons. This seasonal part also could have autoregressive components. Again, it doesn't have any here. It has an integration. So instead of ordinary integration, we now have seasonal integration here. And we don't have any moving average component in the seasonal part. The difference between the seasonal and non-seasonal parts of the model is the reference. Previously, when we differentiated the model, we subtracted the value of yesterday from the value of today. For the quarters, that would mean to subtract a value measured in winter from a value measured in spring. And if you think about all kinds of things you might want to forecast that are dependent on seasons, like for example, strawberry harvests, that's obviously not a sensible thing to do. Seasonal differentiation subtracts the value in the spring of one year from the value in the next year. The model detected that there are 4 seasons. So for this type of differentiation, instead of just jumping back 1 period, it jumps back 4 periods to compare the same seasons with each other. Likewise, for example, the autoregressive and the moving average components would refer in the seasonal models to the error terms and the previous values of data from the same season instead of simply the last period. Finally, there is this remark here with drift. So the model contains a drift. That means a constant is added in each period. You are probably familiar from linear regression as well, with the practice that many linear regression models contain a constant. In time series analysis, this can take on different forms. In theory, you could have an ordinary constant, but in integrated models, having a constant has different consequences than having a constant in ordinary linear models. In ordinary linear models, having a constant, so to say, doesn't do much. It only ensures that the average of the error term will be 0. It is the same for autoregressive moving average models which are not integrated. But for models which are integrated, you have the same phenomenon with the constant that we previously have seen with the error term. From one period to the next, constants and error terms sum up. So if you have a large error term for an integrated model, it means uncertainty is increasing over time. If you have a constant, on the other hand, it means that the overall value of the time series is increasing or decreasing over time, a so-called drift. In our case, it is obviously a positive drift. The value of the time series has increased over time. And we can take a look at how large this drift is by using the report command. As we can see, gas production roughly increases by a value of 4 in each season. We also have the values of the moving average components shown here and can see that all 3 past errors have a positive impact on the present day value we aim to model. Now, the gas production is measured in petajoules, so this is why this result, an increase of 4 for each season, may not sound like a very large number, but it is a very large number. 16 petajoules per year, this is a lot of energy. And these moving average components indicate that if the production was more low or high in a quarter, then the model would have previously suggested it can be expected to remain unusually low or high for the next quarters because these coefficients are positive. Now, it is possible to create a forecast using not only past values of the variable we try to forecast, but also of other explanatory variables. But it has to be handled carefully. The problem with these kinds of approaches is that we are talking about future values. We don't know what electricity production will look like, for example, 2030. We can assume that gas production in Australia may have an input on it because gas can be used to create electricity. But we do not know what the gas production will look in 2030 either. So with these types of predictions, you try to predict future values based on other future values that you also do not know. And for this reason, if you try to include a lot of explanatory variables, you easily include the uncertainty in the predictions of all of these explanatory variables. And that can make such an estimate very uncertain very quickly, because this uncertainty that comes from the explanatory variables will not be visible in the confidence interval. The confidence interval only shows the uncertainty that comes from the y variable itself. That having said, in the case of electricity prices, I think we can argue that gas prices are predictable very well. We have very low confidence intervals here, unless there are some major changes in, for example, environmental regulations or something like that. We can create a fairly well prediction. We just have to keep in mind that it is under the assumption that gas production will develop in a certain way. For this reason, these types of forecasts are also sometimes called conditional forecasts. They are only precise in case that the scenario enters for which they make the prediction, but in case this scenario enters, they tend to be more accurate than a forecast which, so to say, aims to plan for all scenarios at once. Now, we will take the mean from the forecast object for the Australian gas production and save it as future gas production. This is our assumption what the gas production will look like. And it would obviously be very risky if the uncertainty associated with this mean would be high, but the uncertainty is fairly low in this case. So I think we can risk it. The rest of the process is largely comparable to what we have done so far. First, we create a fit, and now we will have to explicitly define gas production as explanatory variable. So now we tell the model create an ARIMA model to explain electricity prices, but consider the gas prices. And now this will be a model which analyzes the relationships between present and past electricity and gas production. We did not include future production yet. We can take a look at this model as well. We see again it is fairly complex. It now has the type LM with ARIMA. So we now have a linear model, a linear regression, where we try to model electricity based on gas production. But we also have this whole ARIMA component, which, as I mentioned before, can become fairly complex. This time we have autoregressive components. We have again seasonal components. Electricity production too has this seasonality with 4 seasons. And we have the influence of the gas production on electricity production, which is positive. Next, we will create and plot the forecast. Again, we will use new data, in this case data on future gas production, to define how many periods in the future we want to predict. And here we now have the forecast. We can see the uncertainty associated with it is a bit more pronounced than it was for the gas production. Electricity production is fairly volatile. It appears to have been more regular in the past with these seasonal spikes. So in newer periods, we have this more irregular fluctuations, I'd say, and they are also continued in the prediction. Still, all in all, it looks as if the model is continuing the present trend. All in all, it looks reasonable. Very well. Now to the last part, which I will just look over briefly because we are already nearing the end of time. I cannot go into details about the appearance of graphs in R. There is another tutorial about that I have given in the past, but in this tutorial I briefly want to show how to label these graphs more accurately and how to export them. So the code below will simply modify the appearance of the graph. It does not do any statistics or something of that sort. It added a title, Electricity Production in Australia, It added the unit, which is very important, as we've seen before, to understand exactly what size we are looking at. Australia, of course, has, as a whole country, a fairly large electricity production. It's measured in gigawatt hours, and it greatly increased over the last decades. Finally, I also added this plus theme BV. BV, that stands for black and white, just because most people don't think that this gray background that is default in Air is looking very nice. But you can do a lot of customization with graphics in Air if you would like to do. To export the plot, we have the so-called ggsave command, which simply allows to save the last plot that you depicted. So in this case, it will be this plot. And to save it as, for example, PNG, simply give it a name that ends with .png. You could also use it to create, for example, JPG or PDF or some other formats. You can also give it any name you want. I just called it my plot. And now we can export it. I don't know why it's giving this error message sometimes, but on the second try it usually works. Now you have seen that under Files, a new element appeared. It's called myplot.png. And now we can take a look at it. Finally, I'd like to draw your attention to the sources. Primarily, this tutorial is based on a single source, which is the book Forecasting Principles and Practice. This book is written by the authors of the AIR packages that I used to create this tutorial, and they go into much more detail on forecasting than I could in this tutorial. The book is available online, completely free. This is the link. You can also find it in the PDF or a Markdown document on the Safe Data Center website. So, if you are interested in learning more, if you would like to try out some other models, for example, so-called exponential smoothing models, which we could not cover here, then I highly recommend you take a look at this.